principles of scalability. Something that feels good to see. Then you can do the correlator.
Very good.
And that Spanish is also it's called up.
That's right.
Yeah.
That passes. Okay, so we still have to understand the resolution of the birthday, which means it's independent of distance period always. That doesn't seem right. I'm back to saying it doesn't seem right. But I can't see the flaw in your explanation. Yeah, to be clear.
Yeah. Okay. So what were you looking for? Looking for the point.
Yeah.
The advancement. That's okay. It's fine. Okay, well, let's get started. It's a pleasure today to introduce to you Markus Luty. Markus got his PhD at the University of Chicago. After the University of Chicago, he did postdocs at Berkeley and MIT. Then he was a professor at Maryland. And then it was too cold on the East Coast and he went to Davis, California, where he's been professor since 2007. And so today Markus has worked on all sorts of things in quantum field theory, famous for a lot of things. But today he's going to tell us about some new work that he's working on dark matter and dwelling in the dark matter with.
Thank you. Thanks very much. So I didn't prepare that many slides, so I hope there'll be plenty of discussion. So this is a project that actually started before the pandemic. Hannah Day was an undergraduate REU student with us. She's now a grad student at Urbana-Champaign, working on dark matter, so I guess I didn't ruin her. And this was also done with Dao Liu, who's a postdoc at Davis, and Yu Zhao, who's a faculty at the University of Utah. So this is the sort of obligatory dark matter introduction slide. You certainly know that dark matter exists. We see its gravitational effects, but we still don't know what it is. And for example, its mass can span many, many orders of magnitude. The sort of first type of model that was intensively studied was a WIMP, roughly in the GeV to TeV range. What I'm going to be ending up talking about is the possibility if dark matter is a boson that's sufficiently light, then it can have a mass anywhere between around an EV and 10 to the minus 22 EV. And this situation here, dark matter today, is better described as a field than as a particle. Okay, but globally, the picture is we have this incredibly vast parameter space, and this is just the mass. The interactions is some other number of dimensions that we also don't know. Okay, so the general strategy that has become what a lot of the field has been focusing on is just to be opportunistic and look everywhere we can with any kind of experiment, right, that seems reasonable. And, you know, with a vast parameter space like this, at least I look at this and I think, you know, what are the chances that we're actually going to succeed in finding dark matter? I'm not sure. I'm not sure that we will. But I still think this is an interesting, even with that point, that's my personal point of view. And even with that point of view, I think it's still very much worth it to do this, because as we're doing this, what we've seen is that it leads to the development of new kinds of technology, tools, experiments that can probe very, very weak forces. And, you know, that's just looks like something that's got to go somewhere. Okay. So I feel like even if we're, we don't know what our chances are, I have no way of estimating, putting a number on it, but even if we don't know what the chances are, this is still a program worth pursuing. And this is very much the spirit in which my talk is going. Okay, so what I'm going to ask is, can we detect the dark matter wind, right? Because we know, or we think we know, what the local density of dark matter is, approximately a third of a proton mass per cubic centimeter. We also approximately know the velocity, because we think that everything we think the whole Milky Way galaxy is orbiting in a cloud of dark matter. So relative to us, the dark matter should have a mass, or sorry, a velocity of around 300 kilometers per second. Okay, and so you can imagine detecting the dark matter wave. You can imagine that it's impinging on some ordinary object. Okay, and of course, if the dark matter just went through the object, there would be no way to detect that, right? So in order to detect it, at least some of the dark matter particles would have to bounce off, and then we would see a force. Okay, so what's the biggest this force could be? The biggest the force could be is if all of the dark matter bounces off, right? And so that's a nice undergraduate physics calculation. You know the density multiplied by the velocity squared, that just tells you the pressure, right, on any object that it hits. And so that maximal pressure is about 10 to the minus 14 newtons per cubic square centimeter. Okay, and that's actually an interesting number, okay, because the forces of this size are actually being probed by current force experiments. Okay, so just to give you some examples, the most sensitive, I believe, depends. Okay, one experiment is the Edbush experiment. Okay, and so it is a torsion balance experiment. It's like a modern day version, improved version of the Cavendish experiment in a sense. Okay, and so here are the basic numbers. The accelerations they can measure are tiny. Here's the test mass. Here's the size of the test mass. And when you put that together, they can measure forces that would be about 2 orders of magnitude smaller than this maximum dark matter force that I talked about. Another example is the microscope experiment. It's a satellite experiment that's designed to test the equivalence principle. It has a couple of masses inside, has 2 masses inside, and it's looking for differential acceleration, different acceleration between them. And here's a picture of one of those apparatuses. The test mass is the cylinder that's living inside here. Okay, and if you put in the parameters for that test mass, they're able to see forces that are sort of 1 order of magnitude smaller than the maximum dark matter force. Okay, so just barely you can see these kinds of forces, but there's not a lot of room for depression. Okay. So in order for the dark matter wind to be detectable, you would need dark matter to interact strongly with ordinary matter in the sense that it bounces off. Okay, because we can't, if we're going to see it with anything like these experiments, we need the force to be pretty nearly maximum. Okay. And you would think that this is just ruled out, right? Because don't we know, one thing we know about dark matter is it doesn't interact much with ordinary matter. That's the one thing we think we know. And indeed, this is true. If the dark matter is particle-like, this is absolutely true. There's absolutely no room for this kind of behavior for particle dark matter by many orders of magnitude. Okay. However, what I'm going to show you is that I claim it is allowed in certain models of wavelength dark matter. Okay, so for light bosonic dark matter, this this kind of behavior is allowed. Okay, so I'm going to just tell you what the model is. Okay, so in this model, the dark matter is a light scalar, phi, and there are a number of possibilities, but this is the simplest one. I'm going to assume that it couples to the standard model by phi squared times n bar n plus p bar p. Okay, the fact that these are both one is not really very important. Okay, it could be a little more one or the other. What I'm talking about, it doesn't really matter very much. Okay, so this is a dimension 5 operator, so it has some coefficient which has dimensions 1 over mass, and I call that 1 over n.
So is there a reason why you chose this one's the marginal one?
So what's really important is that there's a phi squared here. That's super important. I'm about to explain why.
Yeah, so that's why you didn't
Yeah,
choose
so
the marginal.
people have studied this model very much, including people in this room. Okay, but yeah, the more commonly studied model is a version of this where I just have a phi here. This is a Yukawa coupling. Okay, and usually those models have very similar signals. Okay, but it's going to be crucial for the effect I'm talking about that I have phi squared here. You'll see. Okay, so that can be natural if I impose a Z2 symmetry under which phi goes to minus phi. I can forbid the other lower dimensional coupling, so that's not the issue, right? But why is this phi squared so important? Let me explain. Well, here I said it. Okay, this is the thing that people normally consider. We can forbid that with a phi goes to minus phi symmetry. So you may be more familiar with the constraints on the Yukawa coupling. So let me just point out qualitatively what the differences are. So in a Yukawa coupling, a very, very strong constraint comes from fifth force experiment, right? You just exchange one of these phi particles, that gives you a fifth force. If phi is sufficiently light, then you have to make sure you haven't seen that. There are very good bounds on that. But in this model, the fifth force is suppressed. It comes with a loop factor. Okay, so it's somewhat suppressed compared to this. Okay. On the other hand,
what's more importantly, it scales differently with R, right? If phi is massless, the figure on the right decouples as 1 over R cubed.
Sorry, you're exactly right. You're right. That's a much more important effect. Yes, so it's going to have a different power of R, so it's going to fall off much faster, even before you get to the exponential.
So you cannot benefit from building up more mass.
This was one of the people who studied this model. Yeah. Okay. Yes. Thank you. You're absolutely right.
And why is it important for it to be a scalar? Could you make it, for Fermi coupling? Light?
No, it can't be a fermion because once dark matter gets below even I think it's a keV or so, it can no longer be a fermion. Okay. And certainly for it to be wave-like, it can't be a fermion. So that's going to turn out to be important as well. So it is important that it's a scalar. It could be a vector, okay, but it's simpler to talk about a scalar. Okay, but it could be a vector.
Right. Do you have some story for why the mass is technically natural? Like, do you have to worry about?
It's not technically natural. That's my story about that. Okay. Right, just like the Yukawa coupling case, it's just not natural. Okay. So if you may, you may think you can go home if you like. I won't be offended. If it's a waste of your time to talk about an unnatural light scalar, then that's fine. Okay. I might have left this seminar years ago as well. Okay. But now I'm giving it, so I can't be. All right. So that's one thing. But on the other hand, the kind of signal I'm interested in is scattering, right? And so, of course, you have scattering like this for the Yukawa, but the point is you need to put in 2 insertions of the small coupling here, whereas you only need to put in 1 insertion here. So just from that, you can sort of think that maybe you could suspect that somehow scattering might be more important with this model, right? Once you put it out of constraint.
Okay. Markus, can you explain, say a few words, why I can escape the bullet cluster constraints on the.
Let me answer that question later, okay? Because once I tell you more about the model, it'll be easier to answer that question. Okay, but that's a great constraint. That's a great question. That might be the first thing that you think of when you see this. Okay, I will answer that question. Okay, but let me tell you more about the model first and what you don't believe. Okay,
Density is.
actually, no, yeah, I will tell you, okay, I will tell you. But it's not a constraint at all. Okay, all right, so why does this model, how can this model bounce off ordinary matter without, I claim, I'll show later, not run afoul of any other constraints? And the answer is that this model can have what I call a dark Meissner effect, right? The Meissner effect in a superconductor in particle physics language says that inside a superconductor, the photon is massive, okay? And so that's why it doesn't penetrate the electromagnetic radiation. Light doesn't penetrate into a superconductor, okay? So I claim there's an analog of this effect here for this model, because inside matter, this m bar n plus p bar p is non-zero, right? Because we have neutrons and protons in ordinary matter. In fact, this is just equal to the number density of nuclei. Okay, so inside matter, this term gives them additional contribution to the mass of the particle. Okay, right? And nobody's asked me, but you notice that I put in a minus sign here, and I'm assuming F is positive, and so this increases the mass of the particle inside the inside matter. That's the sign that I've chosen. And so I get this extra contribution to the mass. Okay, so now what happens if I have some dark matter wave impinging on an infinite slab of ordinary matter? Okay, so I'm interested in a steady state solution. So I have some wave with wave number k coming in, let's say, from vacuum. So the thing that I have to match, I claim, is the frequency. Right, so the frequency in vacuum is just k squared plus m squared, but the frequency inside here is modified by this mass shift. Okay, so what you can see is that if this mass shift is big enough, it's going to force k matter squared to be negative. Right, in other words, we have exponential suppression inside the matter. That's exactly the Meissner effect. Okay, and so that's what I just said. Right, if k matter becomes negative, the dark matter is exponentially suppressed. And so if you want to put in the numbers, and I just put in something like, I even forget what I put in, I think I put in copper, it doesn't matter. Some pretty, reasonable ordinary matter, you get the F has to be sufficiently small to make that happen. Well, for a given value of the mass here, you can see that it happens in some parameter range like this. Okay, all right. Now, real matter, I'm not going to have this thing be incident on an infinitely large piece of matter because that will have infinitely small acceleration. So if I have some thinner piece of matter, I'm always going to have some transmitted and some reflected wave, right? And how much I have is going to depend very crucially on the thickness, all right? So there's a skin depth, just like in the Meissner effect. And as long as the skin depth is small compared to this L, then I'm going to have a good amount of reflection, and I can get my signal. So that happens then. So the skin depth is just, once I'm in the imaginary regime, it's just 1 over the K in the matter field. And so again, you can see there's some F has to be sufficiently large for that to happen. Okay.
So an interesting regime is when the atmosphere screens it and the satellites don't, right?
Yeah, I'm going to talk about, we're going to talk about the atmosphere, we're going to talk about satellites, we're talking about all this. Okay. All right. So now after you, okay, what are the other constraints on this? Okay. So right here, I'm not going to talk about the bullet cluster. If you really want me to, I can do it. There's no constraint at all. But if you'll let me, I'll just get to it later. Okay, but things that are actually strong constraints in the regime I'm going to be interested in. Okay, there are other constraints in far away in parameter space. One of them is just star cooling. Okay, and the strongest constraints come from supernova cooling from something like this. This is a homegrown Minnesota paper. It's very nice. That gives the constraints on this. And if you translate their constraints to our parameters, they just tell you that F has to be bigger than 10 to the 8 GeV. Okay. Nucleosynthesis is also,
sorry,
yeah.
we like the parameterization where we would write M proton in front, right, and divide by lambda
Yes,
squared.
exactly.
In which case, for all the constraints go exactly like for large extra two model with two large extra dimensions. So the constraints therefore are on the scale of like a 10 TeV or something like that, but the scaling is exactly the same.
Right. That's right. This is just, we just used this. I don't know. This is what we use. Okay. There's also a very important constraint for nucleosynthesis. And here, the point is that phi squared was much bigger earlier in the universe, okay, because it's redshifted till today. And at the beginning of nucleosynthesis, this phi squared contributes to the proton-neutron mass spectrum, okay? And so, and nucleosynthesis cares a lot about the proton-neutron. If you just put in, you can just say, well, you know, I'm going to do something really crude. I'm just going to say we know the helium abundance. The helium abundance is correctly predicted by nucleosynthesis to a percent level. And so this quantity here, delta M nucleon over a nucleon, can't change by more than 1%. You just put in that constraint, you get this. And if you look at much more detailed analyses that take into account lots more effects, in 2015, you get the same answer. And if you do incredibly detailed simulations where you include every possible effect, you also get the same answer. Okay?
I'm a bit confused. So,
Yes.
what's the difference? I saw that your coupling is kind of associated singlet.
Right, but there's an electromagnetic difference.
Oh,
Okay, so even if they were exactly equal, you would still get this. Okay. In any real UV completion, I wouldn't expect them to be exactly equal anyway.
okay.
Okay, but at the level of writing down, you know, log plots, which I'm going to show, it really doesn't make much difference at all. Okay, but yes, I mean, if you really wanted to do exact numbers, you would have to put in all of those kinds of effects. Okay,
So you're saying that even if you are saying that this is isoscopy singlet at some scale and the electromagnetic correction will induce some mass difference.
yeah, because basically it's the fractional mass difference that's telling you the initial thermal abundance, right, at the beginning of nucleosynthesis. That is what is like, that's the source term of nucleosynthesis. Right?
Is it coming from a change in alpha?
No, this is just coming from the coupling that I have. The coupling is phi squared n bar n, right? And so when phi squared is non-zero, that just gives you an extra contribution to the proton. And
Right, but the way you wrote it down, that's going to be an equal contribution to
yeah, but
both.
there's an electromagnetic contribution, right? So what's important for nucleosynthesis is delta m, and you know, delta mn over mn, right?
Sure.
And that ratio is changing when I change it. Okay.
The denominator is changing.
The denominator, like the denominator is changing,
Okay.
right? At linear order, yeah, the numerator is not changed. So yeah, maybe I should have put it as a ratio. Okay. All right, but so this is a very crude constraint, but I'm just telling you, it just agrees with all of the detailed calculations that have been done. Okay, so here's the parameter space. Okay, so this is the kind of plot that you always see in these kinds of light dark matter type plots. Here's the coupling strength. So this is 1 over F. Okay, and this is the mass. Right, of course, it's a log plot. And here are the two constraints that I just talked about. Okay, the supernova cooling and the nucleosynthesis constraints are like this. Okay, so this is I claim. I don't know. I believe there are no other constraints in the current literature in this white region. Okay, so now we can ask, where does the dark matter Meissner effect happen? It happens in this yellow region. Okay, so what I'm requiring here is that in copper, say, I have an exponential suppression of the dark matter field everywhere here. Okay, but then, as I said, I also have to require that the skin depth better not be too large. If the skin depth gets very large, I start not being able to make an experiment. I start having to make gigantic experiments. And so this line right here is where the skin depth is about a centimeter, which I think is a reasonable size where I can, build an experiment. If you want to know right up here against the supernova cooling bound, the skin depth is 1 millimeter. So that's even better. Smaller skin depths are just ruled out at a supernova period. Okay. All right, so this entire region right here, I could in principle, I could have a maximal dark matter force without being ruled out. And you can see this is, several orders of magnitude on the side. It's not a tiny region. Okay. Now, the atmosphere, if you have exponential suppression in the atmosphere, of course, you can't do an Earth-based experiment. Dark matter will never make it to Earth, and that's this line right here. Okay, so this region right here, you could only probe by going into space, but even on Earth, you still have quite a region that you can probe.
But I guess in that case, your experiment must be kind of not within the buildings.
Exactly, exactly. Yes, you're one slide ahead of me. Okay, yes, exactly, right?
Even if you're doing a satellite experiment, do you have to worry about like the interplanetary medium or something screening it out, or?
Maybe sufficiently close to here, okay, but so yeah, you would have to look at that. Okay. I haven't thought about it.
But the overall density of the material is not.
Yeah, I mean, the
So,
densities
yeah,
are certainly far lower than the air. Okay, so I would guess that line might be somewhere here, might even be inside here. Okay, I don't know, but
However, there's a thickness effect. And I agree, maybe bullet cluster because the gas density is too low. There's individual scattering happen at a much lower rate, but it's extended size, right? Just like when I pass through a light through fog, right? And when the fog is when it's long enough, I don't see the laser.
yeah.
So
no,
how-
that's
how-
what
how
makes
can
it. Yeah. But that's what I'm going to talk about. And now I'm going to talk about that, okay, with bullet cluster, gas, all that good stuff, okay? So that was actually the first thing when we realized this was possible, this, dark matter Meissner effect. The very first thing that's the very first thing I thought about is, well, isn't that just ruled? Now that I have this big drag force, doesn't that now rule it out? Okay, isn't that now ruled out? Has this experiment already been done in nature somewhere, right? Some matter is everywhere moving through the dark matter. Have I seen it slow? I probably haven't seen it slowed down. Does that rule out this model? Okay, so just to be obvious, just to put everybody on the same page, here's what our galaxy really looks like, right? There's some stars in the middle, and they're rotating around in this puffy cloud of dark matter. Okay, so everything in the galaxy is moving relative to the dark matter, and so should feel this drag force. Okay, so does that rule things out? Okay, so let's just imagine an idealized situation where I have one object all by itself somewhere out here, and it's orbiting around. Okay, what is its drag force? Now I'm just making the very obvious point here that the force is proportional to the area, the mass is proportional to the volume, and at some fixed density. So the force is proportional to 1 over r. Okay, so smaller objects are going to be stopped faster than big objects for the same density, right? Okay. Now the galaxy has been going for a long time, 10 billion years. Okay, so if we imagine we have our object out there, it's doing this. I have to say it cannot have stopped. If I've seen such an object, it can't have stopped in 10 billion years, right? With this acceleration. And so I can just ask, what size object is that at the density of water? Okay, it's hydrogen, right? And the answer is between this narrow range of 1 millimeter and a centimeter. And the millimeter is here because the skin depth has to be bigger than the object, okay, to get the maximal force, because I'm assuming the maximal force here. Okay, so basically, there are these. So if you say I have a constraint on, golf balls orbiting the galaxy. I've seen that. You see one golf ball orbiting the galaxy. You can convince yourself that it was primordial. Then you ruled out this model. Okay, but things I claim that things like the bullet cluster are perfectly fine. So, for example, the interstellar gas, which is the serious thing, the thing that we see orbiting way out here is interstellar gas, and that does have some particles that have macroscopic size, like nanometers, but not golf balls. And those things they haven't done anything in 10 billion years. So the bullet cluster, I really don't think there's any constraint on it. Yeah.
Sir, why is there a lower bound on R?
Why is there what?
Lower bound on R.
Isn't it smaller
So-
object?
So
The skin
R,
Oh,
so
I see.
the skin depth. The skin depth, right? If R is too small, that's why, so for example, why doesn't the proton? We have lots and lots of ionized hydrogen orbiting around here, okay? I mean, of course, there I should do a scattering calculation, not this classical thing. But, you know, the qualitative conclusion is that a proton traveling through this thing would just never feel any force that you could imagine having. Okay, so I claim that the dark drag force is not a constraint. This experiment has not been done in nature for us. Okay, so we have to do it.
What if the halo is spinning? Does it apply a torque to the galaxy?
Well, I mean, it's already doing, it's already applying a torque to the galaxy, so.
Well, yeah, I guess in the opposite way, but if it's spinning,
Yeah,
What you're
but I
saying,
think
so-
this torque, I'm telling you that this, you can think of it as a torque, but it's just not doing anything to anything that we can see. Okay, so, you know, you can ask about things like, people have asked me about Saturn's rings, people have asked me about asteroids. I think that's all hopeless. There's just nothing that we can say we know has been, you know, orbiting just under the influence of gravity and dark matter for long enough that we can get any kind of constraint. Okay. So now I just want to say something about a time dependence, and if this slide doesn't make any sense to you why it's in this talk, then you're fine. It's just that most of the time when you tell people you're looking for forces from light, scalar, dark matter, they think you're doing something different from what I'm talking about. And what they think about is that, well, phi has these coherent oscillations near us, okay? That gives me a time-dependent force, and so I can see a time-dependent force, for example, in a torsion balance experiment. But what I just want to say is that in the regime where that I showed you before, these oscillations are just far too rapid to see in a mechanical force experiment. That's the point of this slide. So just to put some numbers on this, the frequency is basically the mass, okay? And that's 10 to the 10 hertz. So you could see an electronic signal, maybe at that frequency, but certainly not a mechanical one. All right, so we're really averaging over the oscillations. In fact, there's a longer time scale, which is the coherence time scale, but that's also a short time scale for mechanical experiments. It's about 10 to the minus 4 seconds in the regime that we're doing, okay? So all I'm trying to say here, oops, sorry. I thought I had another thing up there. All I'm trying to say here is that we should think of this as basically we're trying to observe a DC force, okay? There's no oscillatory, at least, you know, the fact of this being a scalar field that's oscillating is not giving us any time scale that is very useful as far as I can see for a mechanical force experiment. Okay.
But this DC force would have annual modulation.
Absolutely. So that's the next thing I'm going to, you're one slide ahead of me all the time. It's my next slide, okay?
going back to that one,
Sure.
so you didn't put the change in time of the amplitude, right? So the amplitude,
This coherence.
no, the phi zero actually, right?
That thing is going to be modulating with time very slowly. So for example, annual or daily modulation effects, things like that will definitely be there.
Well, I was just thinking if it's just getting redshifted.
Yeah, in fact, this is something, maybe I could talk to you about this because you probably know much more than I do about this, is I don't know what is known about, like, you know, how constant do I expect this dark matter wind to be? You know, I don't expect it to be like perfectly constant because just sort of these over and under densities that are orbiting around. Okay, I don't know how, you know, but for the time scale of an experiment like this, let's say we're talking about, I don't know, an hour or something. Okay, so on a time scale like that,
Yeah,
I'm interested in very, very short distance structure of dark matter. I doubt there's anything known
No,
about
that won't change. I was thinking more in terms of, you know, if once you fix that amplitude today today, meaning within our Hubble time,
Yeah.
what was it in the early universe?
Of
But
course, of course.
if
And
this
that's
is a
completely-
virialized dark matter in the galaxy, it
Yeah.
doesn't evolve anymore.
Right.
It doesn't redshift. I mean, like it evolves within the galaxy, like forming a structure and, redistributing itself perhaps, but.
Yeah, exactly.
Not
But it's
redshifting.
exactly, it's very alive.
Right,
It's-
okay.
Okay, so, on average, it's, what the picture I showed, the galaxy is rotating, right? And we know which way the galaxy is rotating, okay? And so we can point and say, okay, the dark matter then should be coming from that direction. But is it exactly that direction? Is it really exactly constant? Just like the actual wind or the weather wind, it doesn't blow at one steady rate. It's always,
But it must, there's still a cosmological component to this.
Yeah, but it's 5 orders of magnitude smaller than the galactic.
yeah, we live in.
Okay, after yeah, absolutely, yeah. I mean, like, the cosmological energy density of dark matter is something like 10 minus 6 GeV per cubic centimeter.
Yeah, that's fine, but,
The galactic is 10 minus 1.
right, but still going back into time, this is, the amplitude is gonna be very different. So I don't know how big of a, well, for anything that I'm going back to really early
Here,
times.
just talking.
No, here it's okay. Yeah, here it's okay.
But absolutely, I mean, it was much bigger earlier, and like I said, that one constraint I know of from that is material synthesis. I don't think, the cosmological history is just, well, in every model of dark matter we had much more dark matter in the early universe. and
Yeah,
that's
but it
part of the
doesn't,
whole
but it
quantum
doesn't couple to
industry
stuff.
works, right?
It doesn't couple to things in this way that you couple them, that's right.
Yeah, I mean, there are other constraints which I'm not even gonna bother to show, but I mean, we worried about, like, one thing you could worry about is, does this drag force somehow affect small structure formation? Okay, because you start forming overdense regions, now they feel this drag force, can it be important? You have objects of all sizes. It turns out that the size of the structures today that have been affected by that are so small, we have no information about them. There are other things there are definitely other things you could worry about that I'm not showing because we just found they did like 0 constraint, ridiculously weak constraint. It doesn't mean we haven't missed anything, but I'm just telling you, we have tried to think about it. Okay. So, all right, so now I'm claiming that if this is going to be detected, we humans have to do it. Okay, and so what are the basic things we should think about? Very basic experimental considerations. Well, the force is proportional to the area, so this is like the world's largest possible violation of the equivalence rate. Okay, so that's relevant because many sensitive force experiments are trying to look for violations of the equivalence principle. So that's just saying this is not at all like gravity. Okay, so this is 100% of this thing is sigma. Okay. The other thing is that is a very distinctive because its direction is fixed in the galactic frame. It's a known direction. It's an a priori known direction that we can use. Okay, we can use that. Okay. The major downside is also the upside of this. Okay, now if I've convinced you that ordinary matter shields dark matter, that's great, but that also prevents me from seeing it, right? And because I'm in a building right here, if the building is going to shield the dark matter, any experiment I do in this building isn't going to find it, let alone some underground experiment. Okay, so I have to worry about these things. So I'm going to tell you about a new window on dark matter, and everybody uses this phrase, but I mean it very literally. What I mean is that the experimental concept is just open your window to let the dark matter in. Okay, so for example, the Edward experiment has this brilliant experiment, but it's in a basement. The basement is a bad place to look for this form of dark matter. Okay, but once you let the dark matter in, you can detect it with a torsion balance. Okay, so as I said, there's a known direction, Cygnus, the constellation. It's in the northern hemisphere, so that's good. So most labs are in the northern hemisphere. Unfair, but anyway, that's how it is. And there's of course a day-night effect, okay, because when Cygnus is below the horizon, the signal has been turned off. Question?
Doesn't all these experiments have a good reason to be in basements? Like-
Yes.
Like it's hard to.
Oh, yeah,
do
you
it
can't
outside
even
of
like the
basement.
airport experiment, you couldn't walk by it, you would mess it, you would walk by it, your
That's what I'm saying,
gravitational
yeah.
force would mess it up.
So what's,
I'm getting there.
okay.
Okay, I mean, so I have to say that I have not talked, I talked to one, I did talk to one experimentalist who works on torsion balancing, and they didn't completely, start cackling with laughter. And so my list definitely is to go and talk with Alberger's group.
They also have to run at night to avoid disturbance from buses going on.
Yeah.
I've heard of, yes.
Okay, so
I heard
yeah,
about
this maybe it's there are very good reasons they're in the base. Yes.
Oh, well, do you know that the direction is actually in Cygnus? Like that's the direction it would be if the dark matter was had no velocity in the galactic frame, but
Right.
it can have some of its own velocity.
Yeah, I think
Like,
as far as I know, we only know this from simulation that the dark matter really is to a very, very good accuracy. You could probably convince yourself with rough estimates. I mean, the idea is that, right, there's a, when the galaxy forms, matter starts collapsing, right? It starts losing energy. There are various instability, whatever reasons why it starts picks a direction, flattens, orbits, all that. But the dark matter does not get dragged along with it. It's just there in its original state. So if your simulations tell you that that is just, a nice stationary thing, then we should be able to get it from how we're orbiting relative to very distant objects.
Couldn't
Right.
you just use microscope results and
Getting there. I don't think microscope is sensitive, but I'll tell you why in a little bit. Okay, let me talk about this first and I'll talk about that. Okay. Okay, so but there's definitely a day-night effect. Like I said, if Cygnus is below the horizon, that's it. Okay, you don't have any effect. There's certainly an annual modulation. Okay, I think we can agree that maybe we shouldn't use an annual modulation as our main signal, but it's certainly there. If you ever saw something, you would certainly want to check that. Okay. And the nice thing about matter being able to shield or block dark matter is that you can easily modulate the signal, right? So it's approximately a DC force, maybe with some unknown time dependence on top of it. But we have the ability to modulate the signal mechanically, okay? And so that's another handle that we have, okay? Now here's the thing that I worry about showing this to experimentalists because they will laugh. Here's the concept, okay? Here's my nice basement laboratory, okay? It's nice shielded, you see the nice thick walls. And here is my dark matter hose, okay? All right, it's just a thick hose. And I can aim it, it's got a nice little horn on it, and I can aim it wherever I want, and see the dark matter wind. And it goes through here, just like light goes through a fiber optic cable, just bounces around in here, and then it comes out into my laboratory when I'm ready for it, okay? Now, here's my torsion balance experiment. Now, the thing is that I need to the torsion balance experiments needs to see a differential force on the two guys, right? It's not good at seeing you push the whole apparatus one way. So what this thing contains, and this was actually suggested by, I should put his credit here, I forget his first name, Terrell, who's a torsion balance guy. So this is supposed to be a platform, and here are some shields, okay? And this platform rotates slowly or however fast you want. And it both modulates the signal in time, and it also, you can see like here, this guy is more blocked than that guy, so it gives you some differential force there. Okay? Yeah.
Does that mean if you have a big ratio between the opening area of on one side of the hose compared to the other side, then you get a huge enhancement because you're
In principle, yeah, that's kind of why I do this, although I didn't do any calculations. It's just, intuitively, it seems like maybe you could get some enhancement by having a big horn out here, right? You could explore that. How much can you gain from that? In principle, you could gain quite a bit.
Sorry, so if you make it larger, then you will also let other particles in, right? Like some
Right, so you're gonna have, I should have put a little shield here, you know, it's not that you can't have any shielding. If you have a little piece of aluminum, you know, most of the dark matter can make it through, but yeah, you don't want hot air blowing in through here.
Since the dark matter is not absorbed, and it reflects from your walls, that
Right.
with time there will be a flux out the same, right?
Yeah, I mean, I guess you could worry that once you fill your lab full of dark matter bouncing every which way, you know. I mean, my feeling is that,
You could still, even if it's absolutely static configuration within the wind, you would modify the force within one skin depth from the walls, right? So you could try to see how, like, say, the two different composition material drop on the floor within the skin depth. And that is going to be like
yeah, any Edbush type experiment would be in principle sensitive. This is the currently most sensitive Edbush experiment. Not exactly this experiment, but a torsion balance with some, you know,
in principle, any differential experiments are good. So, but you could also try what I say, that use the equivalence principle violation, right? And use
definitely
towards the.
Yeah, no, this was just, this was just one concept, just to sort of get the conversation going. I mean, yeah, maybe an experiment, you know, I mean, some versions of the experiment just have different compositions for these two guys, and then they just literally just look for, you know, a torque because of the equivalence principle violation. There are many versions of. Okay, so one thing about this though is that this isn't quite ideal because you might ask, you know, what's the size of this experiment? What are the actual dimensions? I've cleverly not given you any dimensions and not tried to draw it to scale. But one thing to keep in mind is that just that should be dB. I was wondering, what does dN stand for? This is supposed to be de Broglie. Okay, this is the de Broglie wavelength of this dark matter, ranges from 0.1 millimeters to 1 meter in this regime that I'm talking. Okay, so 0.1 millimeters sounds good to me. Okay, it's a nice small wavelength. That's going to bounce around inside here, but 1 meter wavelength is not going to sort of fit in here, right? It's going to be like a waveguide where I'm going to have a big impedance mismatch here unless I make something very, very fancy. So this kind of experiment would probably only be sensitive for the smallest de Broglie wavelengths, which means the largest possible mass. Okay, so very roughly, I would think that it could be sensitive in some region like this. Okay, it could be sensitive maybe in some region around here. Okay, at the largest possible mass. Okay, which is still pretty decent, right? That's still a decent amount of.
But still, I want to discuss this saturation. Right? So suppose I'm talking not about the dark matter, but everywhere you have mirrors and I feed the photons in, right? They're not absorbed, then they just bounce around. Your force is like bouncing around the particles, right? So if I wait for a long time, right, there will be enough of the photons inside so that they will start escaping outside, and there will be at some certain point an equilibrium situation. The question is like the flux of the dark matter out. You don't seem to take that into account. But how does that modify?
Yes, the vacuum is somewhere.
Well, I don't know that you would have to vacuum it. I mean, I'll tell you one thing. I wasn't going to talk about this, but this is what
I'm not saying it's going to suppress things, but it's a factor, right?
Right. No, I mean, let me just tell you one thing about this dark matter that I think is very interesting. Is that, so if you were worried about light going into this room, we let in light, then we you know, close the doors, close the windows, turn off the light. Guess what? The room gets light, right? Why? Because light is being absorbed by the walls, by everything, right? Now, this stuff will never be absorbed. Okay. So I'm actually trying to do the calculation And the answer is smaller than anything I can calculate. So, I mean, basically, this stuff doesn't heat up, doesn't get absorbed by anything. It doesn't lose energy to anything, period.
Therefore, the
And so it
flux,
will literally stay in there forever. You turn out the lights, you close the windows, it'll stay in there forever.
and if you
Right.
wait forever, then the flux of
Yeah.
particles in will be compensated
Yeah.
by the
In
flux. Of
fact,
particles.
you know,
Sorry,
we can go into space, we can go capture a big thing of dark matter, we can bring it back down to Earth. We can open up the window and just have our little detector there. It's not, it might really be feasible.
Well, once the box
It could be a
fills up-
great use of the International Space Station.
Once the box fills up with dark matter, aren't you gonna get the scattering from all directions?
Well, you'd still have the wind here. But
Well,
matter
that's the
doesn't interact
question,
with
is do you
itself
still have
very
the
strongly
wind?
either.
That's called air circulation. We are going to have air
Yeah,
circulation
except
in this
that
system.
here, the dark matter interacts extremely weakly with other dark matter, so
Yeah.
I don't think that's gonna affect the wind.
The wind, the factor bit by whatever your aerodynamic
Yeah.
simulation.
And of course, it goes without saying, this is like every other dark matter experiment. If they don't see any effect, they'll set a bound, you will believe the bound. If they saw an effect, you would never believe it, right? Okay, but then there'd be many, many handles, and it'd be very interesting. We'll worry about that if we have to, right? Okay, so that's the terrestrial experiment. Now, what about satellite experiments? So you asked about microscope. Let me just show you the picture of microscope. So here's a picture. The target is about here. Now, what is all this stuff? I don't know, but it's stuff, okay? And it's like, you know, tens of centimeters of stuff. And I just don't think, the reason the microscope is not going to be sensitive is just that the signal is not going to make it through all this instrumentation, which unfortunately has to be around the mass. So, you know, we did some crude estimates. It just doesn't seem like it's possible. Okay, so it's just not sensitive enough, or it just has too much shielding, if you like. It just obviously wasn't designed for this at all. So,
But by the way, on the topic of like stuff getting into your room, like when you build the room or build the satellite, like isn't there already dark matter in? Right, so,
but it's
yeah,
bouncing around randomly. It's not going to come from Cygnus, right?
right, yeah, but I guess I'm saying if what Maxime is saying is true, then like that happens like right from the get-go. It's not even, you need to let in.
That's right. It's just that you actually need the 300 kilometer per second wind come into your. It's not enough to have dark matter. You need the 300 kilometers per second wind. You can't, right? I mean, I don't know. I mean, maybe, you know, maybe it's, I mean, maybe you don't need the window though, because if you just sort of only let dark matter come into your experiment in one direction, maybe that's actually okay. You know what I mean? Like if I just, instead of having this tube go to outside, I just have it go to another part of the room. Right?
But yeah, I guess
That would be
I'm confused about this point. If I start with a box, which already has some dark matter in, I open a window, dark matter starts flowing in, but like, I mean, can
Bouncing
it,
around
but,
everywhere.
like, and like, it's not just gonna indefinitely flow in, like, isn't some of it gonna go out?
Yeah, there's some.
Eventually, their outgoing
Yeah.
rate will be as big as the inflow.
Yeah, but then like, how do you?
But,
Than your look.
the question will be in the middle of the room, would there be
Yeah, is there a way-
sort of direction? And I don't think that the fluxes will completely, you know, cancel out. There would be some sort of catchment from a whole volume of the room for the
But that'll
particles to
diminish the
flow
effect.
outside, and there is, but the velocities, that's interesting, will be exactly same, right? It's
Yeah,
not,
it's no-
it's not, whatever is leaving, it will be leaving with the same velocity.
Yeah, like Hardy Romani asked me to calculate the energy loss, because they have these very, very sensitive barometers. So you could just imagine, even if it's just heating up stuff a little bit, 300 kilometers per second, hey, that sounds like a pretty decent, actually, that's a terrible temperature, that's another story. But anyway, there's just, I couldn't even calculate it because it's zero to every effect that I was able to calculate, that I usually estimate is zero. Okay, so there's some effect, but I haven't found what the leading. Okay, so this is the region. So, but there is a kind of satellite experiment that would, okay, that I think no one's ever going to build it. Okay, so this is actually an actual experiment proposed by some serious people. So it's not that the experiment is not serious, but I don't think this is just a very expensive experiment. I don't think it will ever be built. But anyway, the idea is very simple. The idea is you just have a satellite that is flying around a little test mass. Okay, and the idea is that this satellite is shielding this test mass from all the crap in the galaxy. Okay, like like the solar wind, radiation, heating from the solar wind, because you rotate this thing to get it evenly heated, blah blah blah. Okay, and then what you're doing is you're checking to see whether this mass is actually following a geodesic. Okay, and so you can look for very long range modifications to gravity this way. So the idea is that you send this thing very far from Earth, very far from the solar system, out away from the planets, okay? And you just let this guy drift and try to see whether it follows a geodesic. Okay? And this can give you the best bounds on, modifications of gravity on an AU, solar system size timescale. Okay. So you have some other satellite that's communicating with Earth. So keep this guy super simple. Okay. And this can absolutely be sensitive in this whole region here. There's no reason why you couldn't. The problem is that far away from the planets is not where NASA wants to go. Okay, so it's just, I've talked to Graham and Grata, they just say, no, forget about it. Okay, but maybe there's, I don't know if you can try the basic spirit of it is that you just need some kind of a sensitive force experiment that you can fly, and it doesn't have a ton of instrumentation or whatever around the test. That's what you somehow would want. Okay. Okay, that's it. The conclusions I have are that the dark matter wind can be maximal in some significantly crazy model, and it may be worth looking for. That's it. Thank you.
Okay, thanks very much, Marcus. Any more questions, Alex?
So I have a naturalness related question. So in the standard model these days, a lot of people don't worry as much about naturalness. People just say, oh, well, it's entropics, that explains the Higgs and the cosmological constant. Amazing.
Yeah.
Is there anything like that for the naturalness issues with these standard models?
Because I do have a backup slide. Okay. So, I put a backup slide so nobody could accuse me of dodging the question. Okay. But I didn't want to put it in the talk with it. Okay. Yes, this is extremely fine tuned. Okay. All right. It's ridiculously fine tuned. Okay, because here, you can just basically close. So here's an example of a model, and this one is actually designed to be a little less fine-tuned. Okay, so I even did a little bit of model building here. Okay, so I'm coupling it to what would be the Yukawa coupling operator in the standard model. Okay, the story is not that much worse for other things, but anyway. And so here I just need to close one loop, and I get a quadratically divergent mass for this guy. And this is many orders of magnitude. Don't ask me how many, but I said many times. Okay, it's way fine-tuned. So only thing I could say about that is just as you said, look, the dark matter abundance is a very anthropic thing, so maybe it's anthropic.
Right.
So,
but then why wouldn't
all right. Now,
why would the dark matter?
I do have one more thing to say, which is kind of, which is that the 5-4 coupling is actually also constrained. This is a little bit less known, okay, but it's a cute thing that in these kinds of models, the 5-4 coupling is very constrained by structure formation. And here the idea is just that, well, this is dark matter, and in the successful theory of structure formation, it's all driven by gravity. So, but if this force is bigger than gravity in some sense, then structural formation just is completely different. You still have structure, so you can't really so cleanly argue that it's anthropic. But I don't know if anybody's actually simulated structural formation dominated by a 5-4 term. Okay, that would be, I don't know. Okay, anyway, I don't think anybody's done that. But if you just require that, you get a bound, a very strong bound on this lambda. which actually completely rules, if you take it seriously, it would rule out most of this parameter space. But actually, that doesn't rule out this parameter space, just because I'm looking at somewhat heavier masses than what people normally consider. So, you know, I just wanted to point this out because I just think this is, well, anyway, Sawdust Demopolis pointed this out to me, and I think it might be worth it. So that's all I have to say about fine tuning. If you really believe in fine tuning, you shouldn't vote for money for this experiment.
Yeah, so why do you actually require this hypothetical satellite to be sent away from the planets?
Well, I think you're just trying to get rid of background. So for the dark matter experiment, it might not be as crucial, okay? Because but remember what they were originally doing is they were looking at the force from the sun, right? And so you want to have the force be dominated by the sun. So you don't want to be in an Earth orbit, right? So they're just trying to get rid of background. Now, for this signal, you're looking for a force that's blowing from Cygnus. Okay, so that is a very, very different thing. And you can, in principle, tolerate having other kinds of forces, right? So, but yeah. So maybe if you were really making a dedicated satellite experiment for this thing, then you might, I don't know, but you might not have to go as far away. And that's a big expense, right? If you look at a scale model of an Earth satellite orbit, here's the Earth, and the satellite is just right on top of the Earth, right? You don't actually go very far to get into Earth orbit. But if you want to go out away from the sun, you have to, that's a lot more, you have to spend a lot more joules of energy to get out of and escape the orbit. So that's a big part of the expense.
Yeah, I have a few questions, but lack of my astronomy knowledge. Does Cygnus go to the opposite direction in the evening? So the Earth does show the way, or it's more northern, so we never have a daily modulation.
Yeah. So actually, you're right. Does it go below the horizon? Actually, I don't think it does in most. So what I'm remembering is that it's visible. I know that it's. I checked to see whether it was visible in Seattle. Okay, and it is, but it isn't. But the range of is way bigger than that. So actually,
yeah,
I suspect you're right. I would never. Yeah, I suspect you're right. It's probably always there.
Yeah, no, we don't.
The daily modulation would then just be the modulation of the direction.
Right, which we don't have much sensitivity unless we have a directional experiment. Right.
Yeah, well, but you do. I mean, the thing is as well. Okay, it depends, right? So in principle, you do. In principle, you are measuring the force from the direction, but once you're starting to funnel it into a laboratory and stuff, then you're starting to lose that direction. But then you can aim it, and you should only see the signal when you are pointing it in the right direction. So, but you're right. Maybe that shouldn't be called a daily modulation. If you're a satellite orbiting Earth, of course, you have a very nice daily modulation, right?
How far north do you know? What is it really north or is it?
Pretty much, if I remember, because I looked it up. Okay, I think it pretty much goes up to the north. I think it goes up to the North Pole. So I think it's
I have no idea.
No,
So
it's always the same spot, whether it's
yeah,
day
so
or night.
theoretically, right? If it's the North Pole, you should be seeing the same half of the sky all the time, right? So it's in the northern hemisphere, so you always see it in the North Pole. Question is, if it were really close to the horizon, right, on the North Pole, see how does it work?
Well, it just depends on the angle that it's right. That it's right.
Yeah, I suspect I'm gonna have to look this up, and I suspect that it does.
If it's 23 degrees. If it's 23 degrees, off from the pole, then it disappears below the horizon.
Right. Exactly. So that I have to check it. I'm not sure.
okay, Raymond.
Maybe Raymond,
Yeah.
we probably should stop.
Just a quick
I'll
question.
have a
So,
copy with anybody who wants. I need a copy. So if anybody wants that copy.
But one more question from Ray.
okay, so if the dark matter is bouncing around the box for a long time, why doesn't dark matter pick up some energy from the box and start to get in thermal equilibrium so that the velocity is actually larger than the matter?
Yeah, I mean, that's this calculation which I'm trying to do, which is to understand how this thing deposits energy, exchanges energy with ordinary matter. Okay, and right now it looks like it's ridiculously inefficient. Okay, so let me say a few words about that. Okay, so if you have an electromagnetic wave that hits matter, what happens? You can just open Jackson as a nice classical effect. The electron starts getting wiggled by the light and then it radiates. It's all perfectly classical. This is a scalar wave. It couples to things in the nucleon. It makes them a little bit heavier, makes them a little fatter. Okay, but so classically, if you're sitting at the bottom of the potential and you're getting a little bit heavier, nothing is happening. Now, quantum mechanically, something is happening because if you're in a simple harmonic oscillator potential and you suddenly change your mass, you are going into an excited state. But how you have to lose that energy? How are you going to lose that energy? The properties of atoms are incredibly insensitive to nuclei. In fact, even if you gave the nuclei a kick, there's something called the Meissner effect, right? That if you were at sufficiently low energy, the entire lattice has to recoil against, not just, okay? So I don't even know what the energy loss mechanism would be. I'm sure it's not zero. Nothing in physics is zero to an infinite number of digits, right? But what is that effect? It's insanely small. So I'm sure that, okay, now there are other versions of this model. This is actually something we are looking at also. We're going to finish this, but it may be different if you're coupling to electrons. Electrons, it's a different thing. That would also weaken the nucleosynthesis constraints. It might open up some interesting parameter space. There, if I'm starting to change the electron mass, now I'm changing every atomic property. I can imagine lots of energy loss mechanisms. That may be more hopeful. So, for example, if you have a molecule, molecules have lots of low-lying excitations. If I can cool them down enough to quiet those things down, I could look at some heating of molecules, or at least see some energy loss or something. I don't know. So anyway, that's kind of, I think that this model is very simple. I think there's, and I'm very confident there's no observable energy loss.
I agree with most of what you said.
Okay.
Actually the walls are probably of the box are hotter than the dark matter.
Yes, they are.
Because
Exactly.
so it's
Exactly.
it's the other way around, right?
Yeah.
You want
Actually, you're exactly right. Because the temperature, if you just turn this into a temperature in Kelvin, and it's like 10 to the minus 5 Kelvin. So you would love to be able to, if you could use it as cooling, it would be great, right? If you could exchange energy with it, it would be awesome. You could have a great.
So maybe you can tune in a very, very small phi to the 4 and somehow build up the density of this. I don't know, from the thermal one.
Yeah.
One also cute effect that could be in the box if they somehow wavelength of the dark matter and the wavelength of the box are kind of similar. Can you kind of have a standing wave of dark matter where the
like I told you, the range, the smallest mass range, the de Broglie wavelength is a meter. I mean, that's like custom designed for your tables are about a meter, right? That's custom designed for a tabletop experiment. So yeah, you could try to resonate somehow,
and then you could try to measure the accelerations of free fall, in the place of the node and in the place of the maximum of the oscillation, and it should differ because the effective mass is for an atom.
Yeah, I should actually check, because the way that the Epworth experiment as a test of the equivalence principle works is really kind of subtle, right? Because I even forget how it works, but you have to do a lot of cross products, and then you see that if there's equivalence principle violation, you'll get a differential torque. on these two masses, right? And it's really subtle. You have to worry, I forget, you have to worry about many things, like the fact that, anyway. And so what the point is that they're measuring a kind of higher order effect. That the equivalence principle violation is giving rise to a higher order effect. But the actual raw forces that their experiment is sensitive to are much better. Okay? And so maybe some effect like this, the fact that if the lab is full of dark matter, there will be some differential drag. I don't know, it might be worth looking at. I don't know.
Okay, I think that was a good discussion, yeah. This is here all day to continue questions, and if anybody wants to go to dinner, please let me know. And let's thank Markus again.